Thank you. Thank you. I would like to thank Wolfgang and Lomei for inviting me, and it's very nice to be back to Bonn. Okay, so I would like to explain some of the common feature of Fallow-Jones and Baum-Kahn. So in Asa's talk, and he explained the long thin cover method. Long thin cover that's in the work of Hotels and look, right? And well, in Lomei's talk, he explains FDC, the finite geometric complexity or finite decomposition complexity. And also in the Baum-Kahn, and the connection, or maybe Novikov. In the talk of Nigel and also Wolfgang. And in one case, one can use also some dimension theory approach, so-called finite asymptotic dimension. So, and I think all those methods have one thing in common, and namely finite dimension in each of those cases. What it does, it provides us, so it provides us with an effective algorithm. For computing K-series. Okay, so this is like the common picture emerging in all the different approaches. So what I would like to do is to introduce some kind of concept which tries to combine all those ideas. Okay, so the concept I would introduce is so what we call dynamic asymptotic dimension. Or complexity. That's going to be a more flexible concept. I don't know if I have time. So this is joint work with Alec and Rufus. Tutti. Yeah. Okay. Okay, so what we are concerned is we have a group. So this is like a countable group. It's a discrete group. And we have a space. With an action. Okay. Now, to motivate our concept, let me first discuss one really extremely nice situation which will enable us to compute the K-series of the algebra we are interested. So So that's the situation of so-called proper action. Okay, let me just. Okay. So this by definition means that the following. And so if I look at the map, and this is proper. So proper means that the inverse image of a compact subset is compact. Now this is actually a very intuitive concept. What it means is that when the group acts on the space, when the group elements are moving to infinity, then it's going to force the orbit to move to infinity. So it's very, very, very intuitive. And one of the nice consequences, for example, the quotient space is going to be a very reasonable topological space. And without this condition, the quotient space can be very bad as a topological space. Okay, now, so this is, of course, the traditional definition. What I would like to do is to reformulate this. That will make my next concept very natural, okay? So I'm going to introduce some groupoid language. Some of you may not like it. Well, for a long time, I resisted the language of groupoid, but it's actually quite helpful in this case. So whenever we have a situation like this, a group action, so we can introduce something called transformation groupoid. Okay. Now, as a set, this is simply just the product of the space with a group. And we want to define some kind of multiplication. And so if I have two elements in this space, I want to define what it means by their product. Okay, so this is only partially defined. It's not defined on all pairs. So the product is just defined to be this, but only if, so when you multiply like this, and the element x is equal to gy. Okay? And so this is the product. This is how we define the product. And of course, once you have a product, then you can have an inverse. And the inverse will be just, if you multiply this element with this, it's going to be x comma the identity. Okay? So this is the so-called transformation groupoid. Okay, so now once we do this, and I can actually reformulate this in the following sense. So I'm going to use the subgroupoid. Okay, so maybe I should say for each say compact subset K of X and finite subset of the group, and the subgroupoid so I will explain what this means. Generated by F plus K. Okay, let me explain what this means. So this is, by definition, it's the closure of the smallest subgroupoid. So it's a subgroupoid of this. Containing Okay. Now, intuitively, you can think that way. So start from, this subset of this groupoid. You just let them, you can multiply, take an inverse, then take the closure. And that will give you this subgroupoid. So it generates this. Okay? And this will be something very nice. So this is, yeah, I should, K cross F. Yeah, K is a subset of, no, I think it's F cross. Sorry. Oh, yeah, okay, so I was looking at this. Yeah, you're right. It's, when in the groupoid notation, I'm using this, so K cross F, yeah.
Do you have a notation for what's the name of the subgroup candidate?
Maybe I say, let me just say, well, I don't know if that's the best notation. Okay. I have not finished, so this is going to be compact subset or subgroupoid. So it's a, so this will be, of course, a compact subset of this, but I'm sorry, it's a subset of this, but it's compact. Okay. Oh, it's just the product topology. G is discrete. It's a product topology. Okay. Now, you see, you can think about the extreme case when X is a point. Say G is finitely generated. So in that case, you see, if you take F to be the finite generating set, in this case, the subgroupoid generated by this will be just the whole group. So it's not going to be compact. Okay, so this is, so it's the opposite of that situation. Okay, so it's something very nice. Okay. Yeah, so when you multiply and multiply, you cannot go very far. Yeah, so you cannot, you are like someone who like your house and you never, well, you only can hang around near your house, okay? But if you have in a situation like an infinite group acting on a point, then after a while, after you multiply, then you get very, very far. You say goodbye, I will never see you again. So that's the opposite of properties. Okay, if you think about this, it's almost a tautology. Okay, it's another way of formulating properties. Okay, any question about this? So this is, I mean, there's nothing deep. It's just the vocabulary, but that will make my next concept very natural. Okay, so now in the bomb-con situation or in K-series, actually what the kind of situation we are most interested in is a group acting on a compact space. So this, proper situation is very rare, and this also, if the group is infinite, then the space has to be non-compact. So that's much less interesting to us. So, but then there's a problem. If you are interested in a compact space, and then, so if G is infinite, then G never acts on X properly. So this is our problem. Okay, so this will never happen. Okay, and so what we will try to do is to introduce a concept which is going to be, in some sense, proper in some scale. Okay, so it's locally, it's going to be proper in certain scale. That's going to be good enough for computation of K-series. Okay? All right, so that of like this action is the smallest such that. So I need to introduce the scale. So for each finite and I can decompose my space so for which each, first of all, each xi is open. Okay, and the sub. Sorry. Oh, this is a union. Okay. I mean, yeah, it's a union. It's not a decomposition. Sorry. Oh, sure. Yeah. So I'm kind of shocked. Oh, this reminded me that I was doing some math with my son. He said, "Oh, Daddy," because he's doing some measurement of me. He just realized I'm very short. So he said, "Daddy, you're a midget." So that happened only a week ago. So I think it never occurred to him I'm not very tall. So. The subgroup generated by okay, which way? Oh, yeah, xi is compact subset. Okay. Now we are mostly interested in the case X is compact. We can. Okay. So to say it's a compact subset of this, it just means that in the group direction, they are only it's finite. Okay. Oh, when I say subgroupoid generated, the way I define it is a closure. The closure of the smallest subgroupoid. Yeah. Sorry. You can actually make xi close if you wish. Then it might be a little bit easy. And it's more psychological to take xi to be open because in dimension theory, that's usually what we do. Yeah, open cover. But that's not a serious issue. Okay. So what I want to emphasize here is, so it's saying that, so this essentially is saying it's proper, it's locally proper in this scale. Okay. Now, so this decomposition actually depends on f. Okay, and usually, yeah. So this heavily depends on f, the choice of f. For a different f, you have to have a different decomposition. If G is no, still you have to, yeah. So you have to have a big set. You cannot just choose the finite generating set. Oh yeah. You can. well, you can choose F to be the ball of radius R. So then it's in scale R. Yeah. That. Oh, yeah, yeah. Yeah, actually, I'm going to make a connection to finite asymptotic dimension. Okay, so let me give you an example. I mean, at first glance, it looks like this, this rarely happens. And but this happens a lot. And well, I will try to convince you for, reasonably nice action. It's always at least for the more general concept, the complexity in the spirit of Loumet. So this is actually more, it happens a lot for things coming from nature. Okay, so now let me give you an example. So the space I'm going to consider is probably not the everyday kind of space, at least topologists would consider. But it's not really very far from Asa's space yesterday afternoon. I mean, it's a little bit worse, but not too much. So, I mean, the example I'm going to look at works in general for finite asymptotic dimension. But instead of talking about the general case, I will just focus on one special example. But this actually works for a lot of groups. Okay, so of course it's not a fancy group. Okay, but it works for all groups with finite asymptotic dimension. Okay, so the space I'm going to take is going to be, it's a huge space. The stone check compactification. Okay, so now I will take, I mean, it does not, we don't lose any generality if I take F to be just, or like Loumet was saying, all elements that, so given, like say R, whose absolute value is. So now I'm going to, in Loumet's talk, so I'm going to, so this is the group of integers. I'm going to cut the group into intervals with equal length. Let me assume R is a whole number. So I'm going to call this 10R. Okay, so I'm going to label it. This is I0, I1, I-1, so forth. So. Okay, so I'm going to now let x0 to be this to k. But taking the closure in the stone check compactification. And x1 to be closed and open. Yeah, this is a totally disconnected space. Okay, so we can check actually. Okay, that's because of the choice of my 10R. Okay, and so you see, if you think about it, when you multiply, and because elements in F has length at most R, so and when you let the group elements like act on one interval, you only shift things around by R distance. So it would never like interact with the next even interval. So it's almost like if you live on each of the even island, and if you are only allowed to move like R distance at a time, so you will never interact with the next island. So if I live on one island, if you live on the next island, my son will never get married with your daughter. So that's a tragedy, of course. But it's good for K theory, for computation for K theory. And because it makes life simpler. Okay. Okay, so this is it's a very intuitive concept. Okay, so now I'm going to explain how we can use this to devise like an algorithm for computing K theory. Sorry. Oh, yeah. So I should add that in the case of stone check compactification, and the action has finite dynamic asymptotic dimension if and only if the group has finite asymptotic dimension. So on the group, this concept is equivalent to finite asymptotic dimension, I mean, with that choice. Now, you might ask, in that case, why do I introduce this concept? And the reason is, in K theory, sometimes we want to choose X to be something nicer than the stone check compactification. Especially, you know, for things like transfer or stuff like this, we want to choose our X so that X has the same algebraic topology of a point or something. And so we want to have that flexibility. Oh, so for any other action, it's yeah, I don't like I mean the extreme case of a point. Oh yeah, you can. Yeah, yeah, yeah. If you have an action on X of this type, then you can pull back. Yeah, then you can pull back. So it's actually on the group having an action on some space with finite dynamic asymptotic dimensions. That's that will imply the group has finite asymptotic dimension. Yeah. Okay, so what we are interested in the following. So again, now we have a space with G action. Okay. So we can form. So of course this will induce. So G acts on the continuous function, the algebra of continuous function on X. Just to make life simpler, let's do everything in the algebraic level without going to system algebras. So I'm going to do CC of X. Well, let me assume this is locally compact. I mean, in the end, we are interested in the compact case. So this is the algebra of all compactly supported continuous functions. X. Okay, so the action, I mean, it's just the standard action. Okay. So we can form, with this, we can form a so-called cross product or semi-direct product. Okay. So this is it's a very elementary construction. So as a vector space, it's just finite sums. So it's a finite sum. So F, G, G. So, and where Fg is. Okay. Now, the interesting information is about this algebra is encoded in the product. So if I have like, well, maybe I just like Fg. So if I can multiply this. So F prime maybe, G prime, okay. So of course, I mean, a more simple-minded product would be just multiply the group elements together, multiply the function together, but we want to encode the dynamics of the action. So when the group element passes through this function, we want to have some action. So which is this action here. So alpha G of and G prime. Okay, so this is a product. Okay, and so our goal is to come up with an algorithm for computing the K-series.
But you're not competing to get this. Just the full algebraic similar product.
Sorry.
This is just the algebraic similar product. You're not competing.
Actually, everything I said works for the compression. It's just I'm trying to avoid the analysis.
Okay, but for me, we will compete.
Okay, so if you,
fine.
yeah, so if you like to complete it, that's fine. Okay, so everything I said, it's going to, okay, everything works for this. Okay. I'm talking about algebraic K-series. But what if I complete it, then I'm talking about topological K-series. The method works for both. Okay, so the only reason I'm doing this is it just to make it accessible. So if for the students, but if you like the analysis, the analytic cross product, this just works fine. Everything works. Okay, so we want to come up with an algorithm. So it's a constructive way. It's an effective algorithm. Okay, so now how do we, in algebraic topology, how do we compute K-theory or any homology or cohomology theory? And what we do is, the most effective way in algebraic topology is, cutting and pasting. So may we tolerate this type of thing. Now, to talk about cutting and pasting, and what we need is we want to have a subspace, right? In classical algebraic topology. Now, in the algebraic context, a subspace amounts to an ideal. Okay. Now, actually, if you think about ideal, especially in the analytic case, and for this kind of cross product, it's actually, it's generically, and we don't have any ideal, okay? And only in very nice situation, like, well, when the action is proper, then you have plenty of ideals, then it's very computable, okay? So maybe let me first discuss the proper case. So the proper case so very special case. If G acts on X properly. Let me make our life even simpler. So assume G is torsion free. Okay. In that case, actually, the cross product is it's very easy. It's the matrix M infinity. By M infinity, I mean the union of Mn. Okay. So all like infinite matrices, but only with at most finitely many non-zero elements. Okay. Of CC of X, the quotient space. So you see, so it's Morita equivalent to some classical space. Now, for us, once we reduce a space to a space, we know how to compute K-theory. So this is the easiest case. Okay. So in this case, okay. Now, what about so now in the case of finite dynamic asymptotic dimension case. So in that case, given a finite subset of G, we decompose. Okay. So, and globally, of course, the action is far from being proper, but we want to look at. So we want to look at the algebra now. The algebra generated by things like this. So this is the semi-direct product But now we only look at elements. So F, G, G. So G, we want G to be in F. We want the support of Fg to be contained. So for each I, let me call this AI. Okay. Now this is actually because of the definition of dynamic asymptotic dimension. When you multiply things like this, okay, your group elements will not go far. Actually, this product, the product structure in this semi-direct product or cross product is compatible with the groupoid structure we talked about. So as a result, if you look at this algebra, when you let elements here multiply and multiply and multiply to generate this algebra, your group element cannot go very far. And it's always contained in some fixed finite subset, which may be slightly larger than F, but not going to be very big. So the structure of this algebra is very well understood. So this algebra essentially is something like this, maybe some big N, okay? And well, so let's see if, let me assume G is tangent-free, just for simplicity. Okay, so in that case, it's just going to be, yeah, so for some space. So it's something which we can deal with, okay? That's what I want to emphasize. All right. So now, but of course, so my algebra C. Sorry. Yeah, it's finite dimensional. So it's a very simple algebra. Okay. So. But we also maybe so if I now look at all those elements, F, G, G and F, G and C, F. Okay, this now can be decomposed as okay. Now, of course, this is just an algebraic decomposition, and so those AIs are not ideals. Okay, if they are ideals, then well, this is something we can handle. If those are ideals, then we can use like some kind of cutting and pasting to compute the KCA of the whole thing. But unfortunately, those are not ideals. On the other hand, they are not very far from being ideals. So roughly speaking, each AI is so I did not define this, but this is an ideal in scale. Did I call this F? Well, let me say this F is like all the group elements. Let me put a proper word metric, a proper length function on it. So, okay, so it's an ideal in scale R. So it's like a quasi-ideal in some sense. Now, okay, I don't want to define that. Okay, so let me almost define that. Okay, so what is an ideal? What is an ideal? So an ideal is something. So if you multiply this with something here, it's still in here, okay? So now what we do is, if I multiply by something with, the group elements is only in F, and you will go out a little bit, but not very far. Okay, so it's almost in that. Okay, it can be made precise. So it's an almost ideal. But it turns out this structure is good enough. This structure is good enough, not for the usual K-series, but for the controlled K-series. Okay, so for each scale, you can introduce like some controlled K-series for. Okay, and of course, the good thing about this controlled K-series is that when I is going to infinity, it's just give you the usual K-series. So these are just K-series elements, who are represented by sums like this, maybe with coefficient in the matrix algebra, but whose group elements has length at most R. So that's what controlled K-series means. Okay.
Not very far. It's not very far depends
on R, yeah. It's only on R, yeah. Okay. So you have to look at, you do cutting and pasting for the controlled K-series. This decomposition enables you to have an algorithm of computing this. Then as a result, we are able to compute this.
So you don't need to have some information on the space Z to know that it's not too complicated in some sense?
Yeah, it's just usual. It's the space of orbit. So when you generate it like this, you see the group. Let me see. So you have the subgroupoid generated by this, right? The group elements, in a way, is acting on this. So you have like a space of orbit, in some sense. So Z is just the space of orbit.
It's not becoming more complicated as R goes to infinity?
No, when we are computing this, we are computing like each scale at a time. So at each scale, it's just fine, yeah. But if you try to do this here, then when I is like going to infinity, you're right, you grow out of control.
The problem will be that even if you can compute just the steps, you have to understand the inclusion. That can be sometimes a problem.
Not here. So here, what you do is the inclusion when R, increased by a constant, and then you get, so you're well. I think in order to compute this, usually you have a left-hand side, which is like real homology. So you're comparing this. You are trying to show there's an isomorphism statement, but the isomorphism statement, it's some kind of controlled or quantitative isomorphism. So it's going to, equivalent not necessarily in R, but in some C times R for some universal constant. Yeah. I mean, it is a good point, but it's not an issue here. Yeah. Okay, I think my time is up. So yeah, thank you. Oh, I want to make one comment. So although the kind of algebra I'm talking about here is not something topologists are usually interested, but a lot of what I'm talking about can be used to derive like integral Novikov type of conjecture. So one of the applications is, and the reason we are choosing, we want to have the extra flexibility of X is that in those integral type of Novikov conjecture, if we are going to apply like Ellick's descent, usually there's a finiteness assumption. But this method will remove the finiteness. So this is an idea coming from Nigel, actually. Yeah, so by choosing the right X, the appropriate X, you remove the finiteness condition on the classifying space. And So that's why we want to have the flexibility of choosing the right X, okay, not just on the stone check compactification. So that's one of the purpose also.
So in connection with that, if you have a good X, you get also a good contractible X?
So that's a very good question. So if I have an X, so of course the optimal thing is to find another contractible X with the same condition. So actually, that's something we don't know how to do. So instead, you have to do an approximation. And things become more and more contractible. And so the approximation, each of the space is not contractible, but contractible in the next space. It's almost like Lipschitz complex, but it's slightly bigger than Lipschitz complex.
But why don't you take the same amount of Kohlmann or the sequence of spaces and you get something contractible? If you have sequence of spaces, one is contractible in the other.
But the issue is that the big space does not have the finite dynamic asymptotic dimension. But each of them has this property. So the dynamics is just does not work out. Yeah.
So the astrological people study, people like Guoliang Yu, they study this concept of finite nuclear dimension.
Oh yeah. This implies finite nuclear dimension. So this is something we are very interested. So there's an issue, of course, like Higgs and Kasparov, method to prove the isomorphism, and but this as in some way relies on the underlying group structure. So that's like choosing a coordinate system. So ultimately, what we would like to have is to have some intrinsic method of computing K theory without having to use the coordinate system underneath. So this is some kind of attempt, but it would be even better just to use finite nuclear dimension. But it does not look like the finite nuclear dimension suffices. So one needs to introduce something slightly stronger. So I don't know for sure. Avi and I had like a concept of finite asymptotic dimension for system algebra, but I'm not happy with that concept. So one should have something, like finite asymptotic, the finite dimension for system algebra. It should be defined intrinsically. So I actually, right now, I don't have a good answer. That's a very good question. Yeah. Sorry, can. Oh, the long thin. It does. So the long thin condition has an extra flexibility, which is the isotropic group can be in this F family of groups. Actually, I did not do that in here, but one can also add that flexibility into here. Then the Bartel-Luck-Reich condition would imply this also. But in order for that to happen, one has to add some more flexibility to this concept to allow isotropic group to be, instead of saying this, what I'm talking about here is essentially, the family of groups is finite. But instead of saying, in the definition, instead of saying that, the supergroupoid generated by xi times f is compact, we would allow the group to be in that family or something like that. Yeah. We allow in the group direction to be something like virtually cyclic, for example, or yeah. So one can allow that flexibility. Yeah. I'm sorry.
Is this notion then more general? Do you have more examples than?
Can go. Oh, you mean with your condition? Yeah, we actually that's not clear. That's not clear. Yeah, your condition, I guess, of course, you don't work on that kind of space, like stone check on compactification. Yeah, but if you allow like stone check compactification like that, then it longs, well, disregarding the finite domination, that part. Yeah, so, well, it was not, we actually thought about this. It was not clear so to us, but maybe so. Yeah, so it's not clear.
So just we understand the answer. So is the question, so you have this covering formulation of asymptotic dimension, you have this coloring, the inversion of these colors, the colors, the one that was given here. They are equivalent. Are you asking if somehow you have the same equivalence in this setting? Because the way you phrased your condition was more inversion with coloring. If you use the coloring instead, you just get exactly what is motion. Was it your question? Because I was not very sure whether I understood the question.
My question was the thing they call B, and actually Guoliang says that we can also do this with an N. You know, that's a condition on an actual
Yeah.
space. And he also said that if my without B is satisfied, then this is satisfied, and the converse is also satisfied.
Yeah, the converse was not clear. Yeah, we called your condition BLR condition, so in our article, so. Patel, look, right, so BLR condition, yeah. Sorry. Yeah, BLI means something. but yeah, oh, so the last thing I want to mention is, that it generalizes to this dynamic complexity. So we were discussing with Lomé yesterday. Is there something funny about?
Well, I have to admit,